let you guys figure that out. At the top, questions at the top. If a person averaged 6.2 meters per second for the entire mile, would they break the current women's mile record of 4 minutes, 12 seconds, or 12.56 seconds? And I don't think it's going to be too terribly long before they break the women's 4 minute, break the 4 minute mile for women. I think there's an unofficial one that's broken the 4 minute, but it's not official. I know there's a wind added one. And I've been contacted by a couple of people about codes for the Cengage. So if you weren't here Wednesday on the Tonkawa side and didn't get your code and hadn't already got it from the bookstore, holler at me. I've got extra cards. If you're over in Enid and you don't have a card and you need it before Friday, I will bring some over with me on Friday again, and but you can always go to the bookstore as well. So they are aware at the bookstore. So people see people calculating and.
Do we have to rejoin the session every time?
Yeah, I think so. I think you have to rejoin the session. And remember, it only takes the first 40, but that's okay. And I got 52 of you. That's not a positive attitude. It's not a positive attitude.
I'm all there. I'll be here forever. R-A-N-K.
W-O-D-B.
Is it case sensitive?
I didn't think it was, but.
It could not be found. Is anybody else? Well, someone answered, so.
Yeah, so it's did you get the 389 in there? Then maybe it is case sensitive. Even if you don't calculate it, you got a 50-50 shot. Still giving you grief? There you go. Okay, at least got one person that's responded A. Thank you for that person, so we know everything's working. All right, everybody think they've got an answer there? I'm not seeing anybody calculating anymore. So let's work the problem and figure it out. Okay, we're going to work the problem and figure it out here. And then I'm going to go over the document camera. Hope everything works. Maybe. Okay, my document camera's on. Let's do this. There we go. All right. Maybe. Okay, there we go. Okay, so the current world record is 4 minutes, 12.56 seconds. And we know that the distance traveled is 1 mile. I'm going to have to do some conversions, which is one of the reasons why I did this, because it gave us fun. It gave us something fun to work with conversions on. And 1 mile is equal to 5280 feet. Inside your end papers of your book, there's a lot of good conversion factors. So that's one of those things that you want to kind of remember. Another thing is I can also look at a mile, and I actually did this one by converting it to kilometers. So I've got my kilometers there. 1 mile is equal to 1.609 kilometers. And just as a refresher, because I know most of you have had general chemistry, this has got 4 significant figures in it. 5280, the way it's written, we don't know if it has 3 significant figures or if it has 4 significant figures. If we wanted to have it definitely know that it has 4 significant figures, we have to put a decimal point, or we write it as 5.280 times 10 to the third. That'll actually tell us that we have that significant figure. Remember that my zeros, when they're like this, they may be a placeholder, so they may or may not be significant. When I teach chemistry, I am extremely persnickety about the significant figures, because the significant figures are going to tell you where the error in your measurement is. Even in physics, as we get further along, I get persnickety about significant figures because it tells you where the error in your number is. But for the most part, in general physics, we're dealing with macroscopic scale of things. So we're dealing in meters per second, we're dealing in velocities, we're dealing in a variety of things. So most of the time, if you report something to 3 or 4 significant figures, you're fine. I don't want to see everything on your calculator, because everything on your calculator just is an impression of it being accurate. Most of the time, we're going to be working in 2 to 3 to 4 significant figures. This first homework assignment that you have due coming up, today was pre-work, but the homework assignment that you have coming up, there are a couple of problems going back to significant figures. So just kind of remember kind of the rules. Placeholders are not significant figures. So if I wrote the number 0.007208, these two are placeholders, therefore they're not significant. That one is significant because it's between 2 non-zero numbers. And so we have that from a significant figure point of view. And so this one, as we have written it, has 4 significant figures. Okay? You do have a couple of problems where you actually have to do the calculation to the appropriate significant figures. If I'm adding, if I'm adding and I have a number that's 3.2, and I add a number that's 5.607. I go ahead and add that. I get 18.807. If I'm in chemistry, the proper reporting is to 3 significant figures because you're carrying where the error is in the number. So you're watching the place, and you're going to carry the lowest place. If I'm multiplying and I do 3.2 times 5.607, my answer is going to be in 3 significant figures because the number that I have is lowest, is in 3 significant figures. So if I'm multiplying or dividing, I go with the lowest number of significant figures. If I'm adding or subtracting, I go with the place. The other thing is that in our chemistry text, the chemistry text that we've been using, the rounding rule is if I have 17.55, I would round this to 17.6. If I have 17.45, I round to 17.4 because I round to always have an even number with 5. But if I have multiple digits afterwards, you can do a different rounding. In physics, it's not as critical, okay? If I'm doing absolutely fine meticulous measurements, that's a different story. But for our calculations in here, we're not necessarily going to worry so much about it. But just as a reminder, significant figures represent my measurement and to the precision that I measured something. So I want to keep track of my significant figures, and but chemistry, it's definitely a big deal. Physics, if I'm doing sophisticated measurements, it's a big deal. But most of the time, we're working in 2 to 3 to 4 significant figures. So my 4 minutes, go back to this. My 4 minutes, 12.56 seconds. I have 1 mile, and we know that 1 mile is 1.609 kilometers. Remember my prefixes, so I can easily convert my kilometers into meters, and I get 1,609 meters. That's my distance. Okay, so my distance that we've got is 1,609 meters. All right, the time. If I do convert that, 4 times 60, 4 times 60 is going to give me 240 seconds. I have to add my 12.56 seconds. So the total time is 252.56 seconds. So my person who broke the world record for the 1 mile, or set the world record for the 1 mile, was traveling at an average speed. If I take my distance, 1,609 meters, and I have my number here, 2.5256 seconds, was traveling at an average speed of 6.4 meters per second. A little more, I could go a little more accurate there, but 6.4 meters per second. This is an average speed. Okay, because we're going to talk about the difference between speed and velocity here in just a little bit. May or not today, but I've done some conversions. I've done a few, did a calculation, and we compared, and our person was traveling at 6.2 meters per second, so the answer was no, they didn't break the record. They were traveling pretty fast, but they didn't break the record. So just kind of have done some conversions. So I can do a lot of conversions. We talked last week that numbers have units, so we want to make sure that our numbers have units. We talked a little bit about my fundamental units. And my fundamental units, just as a reminder, are things like meters for distance, kilograms for mass, seconds for time, seconds for time, kilograms, meters per second that we've got there. We'll use coulombs for charge. And those are all my fundamental units. I have a few others, but for what we end up doing, that's pretty much where we're at. If I'm using English units, this is in feet, this is in slugs, that's still in seconds, that's still charge. Okay. The other thing that this first chapter really focuses on are estimating and getting frames of reference. So I talk about frames of reference, right? We all have frames of reference. I talked about the fact that 27 meters per second is approximately 60 miles per hour. So that gives us a frame of reference. We know that if I look at a floor tile, it's probably a 1 foot by 1 foot distance. So we build ourselves some frames of reference. So we have to look at things in order to make sure that we have an idea of something that is right. A couple of years ago, this statement was floating around on Facebook. Said that there are more atoms in a teaspoon of water than there are teaspoons in the Atlantic Ocean. So the question I have for you, is this a true statement? I'm going to give you a second. Back here. Love it. It's going to be one of those days. Pull real quick. I just put a short question, so I've got yes and no. And we create, release. So is this a yes or a no? Question is, do you believe Facebook? That's always a fun one. I don't know, how many times has Sylvester Stallone died? I find myself now, anytime somebody dies, somebody famous dies, I go to Google and Google it to find out if it's actually true or not. Because we have a whole lot of pieces. Got a good mix of who it is. All right. So now the big question is, in order to prove that or not, I'm going to create one. We're going to do bulletin board. So now, I'm going to ask a question. What information am I going to need to answer that question? Because I can make an intuitive guess, but I got to have some information to answer that question. There's a critical piece of information that I got to know in order to answer that question. How many atoms in a water molecule? That's good. Hopefully we all know that one. Volume of the Atlantic Ocean. Yeah, that's a big piece. I got to know the volume of the Atlantic Ocean. What else do I have to know? I don't know how many molecules. Water molecules in a teaspoon. Okay. How many teaspoons are in the world? I don't know, because I'd have to go back and look at the earth there. Yep. That probably sums it up pretty close. I like that a lot. Okay. Well, we know from one of our MacGyver tools that we're going to always have in the back pocket is that I know the density of water, right? I know the density of water. Density of water is 1 gram per milliliter. So if I MacGyver something, I've got 1 gram per milliliter, so that's pretty good. So I'm going to need something. I'm going to need another piece of information in order. If I know that, I need another piece of information, and I need to know how many milliliters are in a teaspoon, because I don't necessarily know off the top of my head what the density of water is in teaspoons. I do know the density of water off the top of my head in milliliters. So let's kind of work through the problem here. So make me go through this part. There we go. Okay, got that part. Come on. Not letting me. Okay, there it goes. I have to hit it just in the right spot. Okay. All right, so there's some information that we have to know. Turns out the information that I do know is that there's 1 gram per milliliter is the density of water. I've got water is H2O, so I have 3 atoms per molecule. I also probably need the atomic weight, right? So the atomic weight of hydrogen is approximately 1. The atomic weight of oxygen is approximately 16. So my atomic weight is approximately 18 grams per mole. So I've got my 18 grams per mole. So that's a piece of information I'm probably going to have. Turns out I need to know how many milliliters are in a teaspoon. And it turns out 1 teaspoon is approximately equal to 5 milliliters. So now I can do this. So I've got 5 milliliters of H2O, which is going to equal 5 grams of H2O. Because that's 5 because my density. I have 5. If I have 5 grams, I now have 1 divided by 18 grams per mole. I now get 0.28 moles of water. So I get 0.28 moles of water. There are 6.022 times 10 to the 23rd molecules per mole in this case, okay? Because I've got water molecules. So if I do that calculation, I get 1.67 times 10 to the 23rd molecules. But I have 3 atoms per molecule. I have 3 atoms per molecule, so I multiply by 3. And that's going to give me 5.02 times 10 to the 23rd atoms. So we have 5.02 times 10 to the 23rd atoms in a teaspoon. That's if it's pure water, and that's an approximation. So now you understand why if we do some of these approximations carrying a whole lot of significant figures, which is supposed to represent accuracy of the measurement, I'm not that accurate. I'm doing an estimate. Okay, I'm doing an estimate, and there's my estimate. For a teaspoon, I have 5.02 times 10 to the 23rd atoms in a teaspoon. So now we got to do the Atlantic Ocean problem. So the first thing is I got to figure out the volume of the Atlantic Ocean. So I'm going to go to a reputable source, right? I'm going to the National Oceanic Atmospheric Administration. And they tell me that the volume of the Atlantic Ocean is 310.4 kilometers cubed. Okay, so the question is teaspoons in the Atlantic Ocean. Now remember, 1 teaspoon is equal to 5 milliliters. So I'm going to have to do some conversions here. So I do 1 milliliter is equal to 1 cubic centimeter. And 1 cubic kilometer is equal to 1 times 10 to the 15 cubic centimeters. So I can actually come up with the number of cubic centimeters in the ocean. So I'm going to have this as 3.104 times 10 to the 8th cubic. All right. I do my conversion, and it gives me 3.104 times 10 to the 23rd cubic centimeters. So that's the volume of the Atlantic Ocean. But a teaspoon is 5 milliliters, or that's 5 cubic centimeters. So I have to divide this number by 5, and when I do that, I get 6.208 times 10 to the 22nd teaspoons. And we calculated it was 5.02 times 10 to the 23rd atoms. So it's an order of magnitude different for the calculation. So when you're doing the estimate type problems, you've got to figure out what you know and kind of be able to do a calculation. So we could do an estimate, for example, number of heartbeats in 24 hours. I'm going to need to know something. Okay? I'm going to need to know something to figure out or to estimate the number of heartbeats in 24 hours. So things I might question are, is this at rest? All right. If it's at rest, what number would I use for a human? The other thing is heartbeats of what, right? Horse is going to have a little different heartbeat than a human. It's going to have a different heartbeat than a dog. It's going to have a different heartbeat than a fish, right? So we're going to say we'll do an adult human male. All right, we'll do an adult human male. So if it's at rest, what number might I use?
60 beats per minute.
That'd be a really healthy person. Somebody said 60 beats per minute. That'd be a really healthy person. Now, that person I'd have to go over and make sure he wasn't dead, right? So 60 beats per minute.
Healthy.
Huh?
Oh, that's what my dad says, and he's not healthy.
60 beats, resting.
When he's sleeping, he's like,
Yeah, you gotta kind of watch it. Kind of the average that we use is 72 for rest. some athletes can get down to, you really have to nudge them. I mean, they've got a resting pulse rate that it's really, really low. But on an average, we kind of use 72. If I'm doing physical exertion or something like that, we're probably looking at 90. You know, we have all these wonderful charts. So if the person's at rest, we kind of have to know those pieces, right? So the next thing I need to know, that's if we got a beats per minute to start. So we'll just do beats per minute. We'll just use 72 for an average. And so for 24 hours, I got to know the number of minutes, right? So I got to do my conversion. So there's 24 hours. There's 60 minutes in an hour. So if I do that calculation, I have 1440 minutes. And then I just am going to do the 72 times the 1440. This is beats minute. And keeping my unit straight will help me figure out if I have to multiply or divide when I do my unit analysis. And if I do that, I ended up with 103,680. And we're probably okay using that many significant figures. But if I'm doing an estimate, I'd probably say, and this gives me about, if I use that little tilde that says it's about, I'd probably do something that looks like that to give me my estimate for the number. So you could do lots of different things. I mean, people do these kind of estimation calculations all the time. So we get those lovely estimates. I'm going to go ahead and put this up there so that it's in the video and that you guys can see the nice, clean calculation for teaspoons in the water and do the pieces. But there's a lot of fun things that you can look at. The other fun thing about this is these kinds of statements, this can make things sound really, really scary, okay? This can make sound, because of how I use numbers and how I use the various variables, I can make a news story sound extremely scary. Because I can give you the number of atoms, or I can give you the number of, you know, the frame of reference that I'm using. If I tell you a report that it's 2,500 people died, you know, that may be a really scary thing. In fact, that was a news item in the Ponca City paper I guess it was yesterday. It said 250,000 people, 250,000 deaths. Okay, was that due to a hurricane? Was that due to a disease outbreak? Was that due to what? What was that? That was worldwide gun deaths last year. Okay, still don't have a good feel for what that number really means, because I don't know if that counts casualties of war or not. I don't know what that counts. So you can actually use numbers, and this is one of those things you have to watch. You have to watch what those numbers are meaning and how those numbers are used, and you got to watch those units. Because I can tell you, you know, I can give you the amount of salt in a bag of potato chips, and I can give you a really big number. It might be in milligrams, or I might give you as a percentage of the overall weight, which might be a small number. So depending on how they want to color the story, they can actually write bias into the story just by how they get the different numbers in there. Okay, when we left on Friday, we had done our trigonometry in 20 minutes or less, right? Trigonometry in 20 minutes or less. So let's give ourselves a frame of reference here. There's a right angle. This is the angle that I'm going to use. This is the hypotenuse. This is the opposite side. This is the adjacent side. We know that the opposite squared plus the adjacent squared is going to equal the hypotenuse squared. Good old Pythagorean theorem written in a nice, wonderful form. We have the sine of the angle is equal to the opposite over the hypotenuse. We have the cosine of the angle is equal to the adjacent over the hypotenuse. And the tangent of the angle is equal to the opposite over the adjacent. So there's our toolkit. Okay? So let's pretend it's a bright sunny day. It's not a bright sunny day today over here in Tonkawa. But let's pretend it's a bright sunny day. And I have a flag up here. And it's casting a shadow. There's my casting a shadow. Okay, so this is the shadow here. So we got it shadowed over here. And I can go over here and I can put a protractor right here. And I can eyeball and line up my sight to the top of the flagpole. It's pretty easy to measure this part. I can actually go out and use a meter stick and measure this part. So let's say I go out and use a meter stick and measure that part. And I measure that shadow to be 1.78 meters. I've used my handy dandy protractor and I've measured this to be 37 degrees. I want to know the height of the flagpole. So what I've got here is I want to know the opposite side of the flagpole. I know the adjacent side. And I know the angle. So if I go to my toolkit, I'm going to probably, I want to know the opposite and I know the adjacent. I'm probably going to use the tangent. So I'm going to use the tangent of the angle. Multiply the adjacent times the tangent. It gives me the opposite. I can now, if I want to write this, this will be my x times the tangent is going to equal y if I use the vernacular that the textbook is going to use. I've got my lovely little variables there. And now I can plug in my numbers. I have my 1.78 times the tangent of 37 degrees. Going to equal my value. One of the things I have to do on my calculator, let's see if I can get this to. One of the things I have to do on my calculator, depending on which calculator you use, is make sure you're in degrees. Because I could be in, let's see, I'm so happy. I could be in radians or gradians. And if I'm in radians, I'm going to make a mistake and I'm not going to have anything work the way I want it. When we get to rotational motion, you'll see that we'll need to be in radians, but right now we want to be in degrees. So I'm going to take the tangent of 37 degrees. It's going to give me a value. And I'm going to multiply that by 1.78. And that's going to give me a value of 1.34 meters. So I may not be able to, in these numbers, I could probably have measured it with a meter stick because I just pulled numbers out of a hat. But I could measure a building. I can measure a billboard. I can measure a lot of things just by using the trigonometry. Okay? Just by using the trigonometry. There is a page in the back that also gives you some other trigonometric type things. But you guys have a homework problem. And the homework problem looks like this. We've got a mountain, right? We've got a mountain. And we have a person over here that's looking at the mountain. And we're going to make an assumption that we're like coming from Lyman, Colorado to the Rockies, right? You see the mountains long before you actually get there. We're going to make the assumption that she's traveling on level ground, and they can sight the top of the mountain. we have some information about that. We know that this person then moves here. And now the person comes out a little later, and then they site the top of the mountain. Okay? I think we have information like we know this angle, we know this angle, and we know this distance. Basically what I've done by drawing my picture, you now have a way to look at this distance here. I can say that this is a distance D. So this distance for this side is going to be X plus D. This distance for that side is just going to be D. And then depending on the information that I want, I can set up my tangent of the angle, which is going to be my opposite over the adjacent. And then I can proceed to do some calculations. Okay? This problem seems to cause people a lot of grief. So one of the things you want to do when you start doing a physics problem is draw your picture. All right, I've told you I'm going to use Scantrons for the tests, but I also told you that I will give you partial credit. Okay? One of the things you get partial credit for is drawing the picture for your problem. So, if you draw your picture, and it's a decent picture, you're going to get at least a point. So that's really something you want to think about when you draw your problems, if it's appropriate, because there will be some questions, things like, what's Newton's second law? And I give you a multiple choice, and you'll be able to go, okay, I know Newton's second law or I don't, but we want to be able to look at it from that perspective. But draw your pictures, because your pictures are going to help clarify a whole lot of pieces of information. So why do we do, and why are we worried about our sines and cosines, and worried about our different pieces? Well, one of the reasons we worry about it is because we're going to deal with something called vectors. Okay. So we're going to start looking at vectors. Okay. A vector is something that has direction and magnitude. Okay. Vectors have direction and magnitude. So let's do this. This is going to be, I've got a house. I have a house. I have a house. So this is going to be like a little map. I got streets. I got another house. Got another house. I got another house. And we're going to use our little, this is north kind of thing. I could have a person. If the person travels 2 houses to the east, so this is going to be the distance of 2 houses to the east. I've got a vector that goes to the east, and its length is 2 houses. Okay? The length is my magnitude. So how big this is my magnitude. Then that person is going to travel north 1 house. So we go north 1 house. And then let's say we go, we're going to go west 1 house. I can now ask several questions. One is I can ask the position that we finished from the start. So if I started here and I finish here, I can look at the position here. I didn't draw that very well.
Much better than what I.
Here's my picture. Okay, there's my finish. Okay. So the position that the person currently is in is one house east and one house north. I've given you kind of an endpoint position. So as the crow flies, that's where I ended up. Okay, so I give you a position. This vector now has a magnitude, and we can figure out that magnitude, right? I can figure out that magnitude because a squared plus b squared is equal to c squared, and this is 1, and my funny units here, this is 1 squared, and 1 squared is equal to 2, right? So c is going to equal the square root of 2, and that's the length. I'm sorry. That's the length that this person, that's the change in position that this person actually took. Okay? That's the change in position that this person actually took. But I've got that vector. All right? If I did this in x and y, so we're going to use this in x and y coordinates. I used it as walking around the block kind of thing. But if I use this in x and y coordinates, I've got a person that traveled 1 in the x, 1 in the y, and I could write this as 1 in the x direction, where I is a unit vector in the x direction. Okay? I has a magnitude of 1, and I have to write whatever the magnitude is in front of it. I have the next one in the j direction. J is in the y direction.
You need to move the paper up.
Okay,
Thank you.
there we go. Yeah, so I have different screens. So even though we could see it over here, they couldn't see it over there. So I have a vector in the I direction and a vector in the j direction. And that's going to give me my result. This is going to give me my result, and this is equal to my vector c, or my vector, if we call that vector c. That's going to equal my vector c. Now my vectors, we write vectors, we can write it like this, have a little arrow over it that tells you it has direction. And when I add vectors, I add them head to tail. So in this case, so if I look at this, go back here, if I were to write this vector, this first vector is 2i, because it's got a magnitude of 2, and it's in the I direction, and we typically call this the positive side, and we call that the negative side. That vector was 2i. Same with here. This is usually the positive side, and this is usually the negative side. So this vector right here was 1j. And this vector right here was minus 1i. So I can use my vectors in these component forms, and that's what these are. These are component forms, and I can add them. So I did 3 vectors, so I'm going to add vector A, vector B, and we'll call it vector D, because I use C for a different vector. Vector A was 2i, vector B was 1j, and vector D was minus 1i. When I do this, I can only add the i's together, and I can only add the j's together. So now my vector C is going to look like 2 minus 1 in the I direction plus 1 in the j direction. And when I do this, I get 1i plus 1j.
It's not up there.
We lost it. I lost Enid. Hang on. I know what happened.
Don't mind it.
all right.
And she's been with it since like
No,
Saturday.
my dad sent me to school with a broken collarbone because he thought I was just complaining. He felt bad. We've all had it. We all do it. You're not hurt.
No.
You're not hurt. Get back up on the horse.
I'm hurt. But I got hurt. So loud.
Yeah. Yeah, I can pause. Let's pause it. See if that works. Okay, looks like we got that part. Looks like we got the document camera. Okay. Now, when did we lose them? We lost them as I was doing this edition?
Yes.
All right, that's when we lost them. Okay. This is also the fun part. So you guys get to experience both sides because I go over on Fridays. So what we do is we can only add the I parts together, and we can only add the J parts together. All right. So we can do this. This is called the component form of the vectors. So this is a nice way to be able to add vectors. When I add vectors, I do them head to tail. Okay, just like I did. Now I did it very simple here. But I can do vectors in a lot of different other ways as well. So let's kind of look at our vectors. So rather than using funky units, let's just kind of draw a vector on the page. So this is a vector. So I've got this vector. And I have my coordinate system to kind of look at my vector. So what we were talking about the other day was that I could have two types of coordinate systems, right? I could have my Cartesian coordinate system, and I could have my polar coordinate system. So I've got a vector here, and we're going to put this position, just for grins and giggles, I've got this at 3 in the x direction, and I've got it at roughly 2 in the y direction. So the end of the vector is written as a 3, 2. In its component form, and we're going to call this vector A. In its component form, A would look like this. A is going to be 3 in the x direction and 2 in the y direction. So I can write that vector in its component form. Now we converted on Friday between polar coordinates and Cartesian coordinates. So if I wanted to find R, I wanted to find the length of A. So if I wanted to find what we would have called R for our polar coordinates and my angle for my polar coordinates, turns out R is going to equal what we call the magnitude of A, and that's why I've got the absolute value there. And we know how to do that. That's the square root of 3 squared plus 2 squared, which is going to give me 9 and 4. Just a second. 9 and 4 gives me my 9 and 4, which gives me the square root of 13. So my R component, if I were writing in my polar coordinate system, that gives me 13. But that's also the magnitude of that vector. Okay? That's also the magnitude of that vector. I can find the angle, right? My angle is going to be the arc tangent of my y, 2 over 3. So my angle, if I plug that in the calculator, yeah, go ahead and have a seat. No problem.
My alarm didn't go off.
It's okay. 33.7 degrees. Okay? So that's one way that we can do the polar coordinates. So I can look at my different pieces. Well, I can give you a vector, so that's how I go back and forth, but it turns out if I look at this right here, that's my y projection, this right here is my x projection. So I can use my trigonometry in order to give myself my components back and forth. In order to work with my particular pieces there. So I can write this. So if I gave you a vector, so we'll give you a vector. This time I'm going to use a vector like this. There are my components, right? And I'm going to give you that the vector has a magnitude oh, we'll just, for grins and giggles, say 5. And I'm going to give you this angle. That is 64 degrees. And what I'm going to end up doing is I'm going to write the vector in its vector components. Okay, I want to write it in its component form. So I want to write this vector A in terms of what it is in the x direction. This is a unit vector, means it has a magnitude of 1, but it tells me it's in the x direction. And I have the component in the y direction. So that's what I'm after. So how am I going to do that? Well, this is where it comes in. We go back to our handy dandy Phys. Okay, so we know that this has a magnitude of 5. So this side is my opposite side. The sine of the angle is equal to the opposite over the hypotenuse. So I want to calculate the hypotenuse times the sine of the angle is going to give me the opposite. So if I do that, I'm going to have 5 times the sine of 64 degrees. If I plug that into the calculator, and if I didn't mess up, I get 4.49 as my value for this projection. Okay? 4.49 is my value of that projection. Now if I do this side, that one's the adjacent. I'm going to do the same thing, except now it's the hypotenuse times the cosine of the angle. So if I go back and I find my handy dandy toolkit, there's my handy dandy toolkit. Let's see if I can scroll out a little bit. Okay. All right. See if I can move that just a little bit so you can see everything on the same screen. There's my handy dandy toolkit, so you get the opposite there. So if I do that, that's going to be 5 times the cosine of 64 degrees. Gives me 2.19. So now I have at least the magnitude of that projection. But remember, I want to write it in terms of my components. So if I write it in terms of my components, I have to take into account the direction now. Okay, I have to take into account the direction. My adjacent side is in the negative direction on my coordinate system. So I have to put a negative value in here. And I have to put the positive value on that side. And now I've gone from a polar coordinate system to a Cartesian coordinate system. And if I want to position this point, that point is minus 2.19, 4.49. So vectors have direction and magnitude. Now if I want to add another vector to this, I'm going to add them tail. So I could add that vector to it. And let's say that this vector B, happens to be, I've drawn up to scale, but I got 3 in the I direction and 1 in the J direction. Now I want to know what the resultant vector is. This would be my resultant vector. And we're going to call this vector R. That's going to be my resultant vector. So let me write, I'm going to write it over here. So I'm going to have B. I'm going to line up my I's and my J's. My resultant vector R is going to be 3 minus 2.19. Gives me a plus 0.81 in the I direction, plus 5.49 in the J direction. I can find the magnitude of the resultant vector. Hang on, I will get it up. The magnitude of that resultant vector is going to be the square root of 0.81 squared plus 5.49 squared. Square that plus 5.49 squared gives me the square roots, just so you guys have the extra pieces, 30.8 gives me 5.55 is the magnitude. And to calculate that angle, and this would be the angle, and I'm going to use phi just to make it have the different angle. I can calculate phi. Phi is going to be the arc tangent of my 5.49 divided by my 0.81. And that gives me something on the order of 81 degrees. Or 82 degrees if you round it. So 82 degrees. So by drawing my picture, if I were to draw it to scale, I could actually use a protractor and measure that. I didn't draw it to scale, but I could actually do that measurement and be able to look at it that way. So when we start talking about motion, one of the things that we have to learn about motion is certain things are going to be vector quantities. They're going to have magnitude and direction. Speed is not a vector quantity. Speed is just a value. Speed just has magnitude. This is where we're at. All right. I'm going to stop there because brains are full. I did get stuff recorded and posted, so it's posted. We don't do